Hello everyone, this is your Test 5 review. We're going to start with problem number 1. Does a newsletter publisher believe that more than 72% of their readers own a laptop? More than 72%, that's usually more than, less than, that's pretty important in the problem, or equal to, or something like that. There is sufficient evidence at the 0.05 level to substantiate the publisher's claim, or is there sufficient evidence? All right, state the null and alternate hypothesis for the above scenario. So what you want to do to state a null and alternate hypothesis is you want to write down the claim as it's given. So 72%, that's a proportion. So that'll be P is greater than, and 72% as a decimal is 0.72. And then we want to write down the opposite of that. So what would the opposite of greater than be? Or more than is greater than. You'd probably say just less than, but whenever we write down the opposite, we always want to write down less than or equal to. Because if it was equal to 0.72, that isn't greater than 0.72. So equal to is also included whenever you write it down the opposite way. Okay? Now, you take these two, the one that has a equal to sign in it, that's going to be your null hypothesis. Okay, so that's your H sub O. That's how we denote the null hypothesis. So it's H sub O, and then this colon just means like where P is less than or equal to 0.72. And so the other one, that's the alternate hypothesis. So our H sub A, which stands for alternate, that's going to be P is greater than 0.72. Now, it's important that we understand what the greater than in the alternate hypothesis actually means, but on this particular problem, we only have to state the hypothesis. So as we move on, the symbol that's with the alternate hypothesis is going to make a difference, but on this problem, that's all we needed. So that you just fill in the blanks on this number 1, and you get your answer. All right. This one again is state the null and alternate hypothesis. So even though it has a lot of different numbers here, you have a mean in here, you have a N of 290 engines in a sample, we only want the null and alternate hypothesis. So really that's what we're looking for. What is the problem itself asking? So read through the problem and you'll see, let's see, if the valve was designed to produce a mean pressure of 5.9 pounds per square inch, is there sufficient evidence at this 0.01 level that the valve does not perform to the specifications? So is not equal to. So here's the, let's see, here's the mean pressure, 5.9 is what it says the valve was designed to do. And we're trying to figure out if it does not perform to the specifications. Okay. So does not equal 5.9. That's how I interpret that. So mean, remember, that's mu, does not equal, some of you may not have ever seen this symbol here, equal to with a slash through it, does not equal. And then it was 5.9. Now the opposite of does not equal would be equal. So the null hypothesis is always going to be the one with the equal to symbol in it, or the equals symbol, like the problem before. So our null hypothesis is going to be P equals 5.9. And so that leaves our alternate hypothesis to be, not P, I'm sorry, mu. Is not equal to 5.9. So you just kind of got to sift through the information to find the null and alternate hypothesis. Okay. Problem number 3. It's basically the same. You see, we just want the null and alternate hypothesis. So we have to figure out what is the problem asking. So if you read through here, it says, it is believed that the machine is underfilling bags. So what would that actually mean? So it's believed that the machine, if it's supposed to, it says it's supposed to be filling bags correctly at 445 grams. But it's believed that it's underfilling bags. So that would mean that the mean would be less than 445. Underfilling, so that would be less than. So on this one, the mean is less than 445. The opposite of that would be the mean is greater than or equal to 445. And so the one with equal to, we'll see that's going to be our H sub O. So that in H sub O is the null hypothesis. So the null hypothesis is mu is greater than or equal to 445. So that would leave the alternate hypothesis to be mu is less than 445. And the symbol in the alternate hypothesis, like I was mentioning earlier, that does have something to do with the test statistic, which this problem doesn't ask anything about a test statistic, so we're not worried about the symbol in the alternate hypothesis, but just keep that in mind. It is important which one is the null and which one is the alternate hypothesis. All right, moving right along. Problem number 4. All right, so this problem says find the value of the test statistic. So we need to figure out, what are we dealing with? Are we dealing with a mean? Are we dealing with a proportion? Are we dealing with a standard deviation? So we have to figure out what type of test statistic we need. All right, so an engineer has designed a valve that will regulate water pressure on an automobile engine. The valve was tested at 110 engines and the mean pressure was 4.5 pounds per square inch. Assume that the population variance is 0.64. The engineer designed the valve so it will produce a mean pressure of 4.7 pounds per square inch. It is believed that the valve does not perform to specifications. So this is another one of those does not equal to problem. A level of significance of 0.05 will be used. We don't need that, I don't believe. We would need that if we were trying to figure out more, but all we're trying to do is the test statistics. So it looks like we are dealing with means because that's what it's given us, a mean here and a mean there, and it gave us a variance. So the formula for the test statistic, as long as this thing has an n of greater than or equal to 30, or it tells you in the problem that it's normally distributed. So the n here is 110. We've got a lot of things we need to write down. N is 110. That is greater than or equal to 30. So we can assume this will work correctly with our test statistic. It is normally distributed. So let's write down first the null and alternate hypothesis. You may say, why do I need that? I don't really need that, but it's okay to practice. So we're going to assume that the valve is not working at specification, 4.7. And so that would tell us that the opposite of that is equal to. And so our null hypothesis is going to be mu equals 4.7, and our alternate hypothesis is going to be mu equals, or not equal to 4.7. All right, so the other values in the problem that are going to be important to us, you're given a sample mean, right? Because in the problem, we had 110 engines, with a sample mean of 4.5 psi. So the sample mean is 4.5. The number of engines, your N here, is 110. And we were given that the variance this is the population variance is equal to 0.64. Now, the way that we find the test statistic for a mean, if it's normally distributed, the test statistic z is equal to x bar minus mu over mu sub x bar. And remember, mu sub x bar, I'm just going to write it as, sigma sub x bar, not mu sub x bar. Sigma sub x bar divided by the square root of n. All right. So we have our mean from our sample, 4.5, minus the population mean, or what it was supposed to be working at, 4.7, over, now we're not given the standard deviation, we're given the variance. Remember, the standard deviation is the square root of the variance. So if you say the square root of 0.64, then you're going to get 0.8. All right, so that's divided by 0.8 over the number of engines that we looked at was 110, so it's the square root of 110. Now, I'm not going to go through how to do all of this. You should be able to punch this in a calculator. You can actually, since this is a fraction, you could flip and multiply this times 0.2, because that's what you get in the numerator. But you should get about negative 2.6220, and it keeps going on forever. So the problem says to round to 2 decimal places, so it's negative 2.62. Round right here, it cuts off there. That's your test statistic. That's what we would use if we had a critical number in order to figure out whether to reject or to fail to reject the null hypothesis. But all it asked was for the test statistic, so that's all we're going to do. All right, problem number 5. An automobile manufacturer claims its van has an average of 37.4 miles per gallon. Man, I would love that van. That's awesome. Independent testing firm has been contracted to test miles per gallon for the van, since it's believed the van has an incorrect manufacturer's MPG rating, which is probably right. After testing 280 vans, they found a mean miles per gallon of 37.8. Wow, that's great. All right, so we're given the standard deviation and we're given the significance level, but all we want is the hypothesis. So we're given a lot of information we don't even need. We just have to figure out, what are we testing here? Okay. So we were given miles per gallon, which is an average. Okay, so we were given that the average miles per gallon, or the claim is 37.4. It says the independent testing firm has been contracted to test this, and it's believed it is incorrect. So we write down what's given. The claim is that it's not 37.4 miles per gallon. Okay, and so the opposite of that would be that it's equal to 37.4 miles per gallon. So the one that has the equals to, that's going to be our null hypothesis. And the other one, that's going to be our alternate hypothesis. All right. So that's it. There's nothing else to do. It gave us all those other numbers, but we only wanted the null and alternate hypothesis. Moving right along to problem number 6. Let's see. It looks like here we're going to try to figure out the critical number. The critical number is the value that kind of draws a line between whether we accept or we reject or fail to reject the null hypothesis. Okay, and so the critical number is going to come from two things. First, you need to know from the alternate hypothesis if there's a greater than sign, a less than sign, or a not equal to sign. Because there's three different tables in your book that you'll get your values from. There's other ways to figure it out, but I would use the tables. The tables make this a lot easier than using formulas to figure it out. So what we need to do is first state the null and alternate hypothesis. So this problem says, an engineer designed a valve that will regulate water pressure on an automobile engine. The engine designed the valve such that it would produce a mean pressure of 5.2 pounds per square inch. It's believed the valve performs above specifications. So above would mean greater than. The valve was tested on 120 engines, and the mean pressure was 5.3 pounds per square inch. Assume the standard deviation is known to be 0.5. That's the standard deviation. You can give us variance, give a standard deviation. A level of significance of 0.01 will be used. Okay. I apologize if there's some background noise. I'm using my tablet to do this, and it does cause a little background noise, so you may have to turn your volume up a little bit. All right, so we need to write down the null and alternate hypothesis. So it's given in the problem that it's believed that it's performing above specifications. So above would be greater than, and the number was 5.2. The opposite of that would be less than or equal to 5.2. So the null hypothesis then is going to be quality, 5.2. The alternate hypothesis is going to be the other one, greater than 5.2. Now this symbol right here is very important because this tells us whether to use, there's three tables in your textbook. They are around page 484, somewhere around that area. One of the tables tells you if it's a two-tailed test, use this table for the critical value. If it's a greater than, this would be a one-tailed test with greater than, then use that table. And then if it's less than, use that table. So I don't believe I can pull that table up. It may be in here somewhere. And you may be able to find it. But I would look in your ebook and just have that open to around 484. So anytime you need to find a critical value in any of these problems, you're going to need those tables. So just keep your ebook open up to around, or either print those out, maybe open it up and print those out so you'll have them during your test. Because I don't think you can pull your ebook up and have your test open at the same time. So this greater than tells us to use that table that's going to give us a critical value of what? Well, it depends on the significance level. So the significance level is at 0.01. So you look at your table, your greater than table, and then you look at the significance level of 0.01, and you'll see a critical value, and this is a critical Z value. I've seen it written in several ways. If you just want to say critical Z, keep it straight, that's fine. I've seen Z sub C, that would mean like critical Z. I've seen Z sub alpha, I've seen Z sub alpha over 2. There's a lot of different ways that you can write it. So the critical Z, though, here from the table is going to be 2.33. Since it's a greater than here, all of the greater than values, you're looking at the table correctly, have positive critical Z scores. Because greater than, remember, it was kind of like area to the right. You think of it like that to kind of be a hint as to what side. So what does this actually mean? even though we don't need to know what this actually means. That's all we need for the problem. This means that under the normal curve, there's a value, a z-score of 2.33 that will, it's like a dividing line between the values that will be okay so that you do not reject or fail to reject the null hypothesis, and then any value over here. So if we got a test statistic in here, then we would reject the null hypothesis. So if it was 2.4, 2.5, 2.6, and so on forever, we would reject the null hypothesis. Okay, now did you need to know all that for this problem? No, but we do have to know that for problems down the road. So maybe listen to that a couple of times and maybe it'll make a little sense. Don't worry though, we will get some more problems doing that. So let's go ahead and move right along. That's our answer, 2.33. So if z is greater than 2.33, that's the critical of this, that's the critical region. Okay. I believe that's even z is greater than, and you put in 2.33. All right. So this problem, we are trying to find the test statistic. So we don't need a lot of the other information. It may be okay to write it down just to practice. This is problem number 7. It takes 95 hours to receive a basic driver's license. A new license training method uses computer-aided instruction has been proposed. The researcher used a technique with 170 students and observed they had a mean of 94 hours. Wow, big difference, right? Assume the variation is known to be 49. The variance is 49. A significant level of 0.01 will be used. Determine if the technique performs differently from the traditional method. Find the value of the test statistic. So that's all we want is the test statistic. Your N, your 170 students from your sample, that is greater than 30. So this will be a Z test statistic. Z equals X bar minus mu over, remember it's sigma sub X bar. So it's actually sigma divided by the square root of N. So those are the values we need. We need the mean from the sample. We need the mean from the claim. We need the standard deviation, and we need the N from the sample. All right. So let's write those down. And like I said, it wouldn't hurt to go ahead and write down the null and the alternate hypothesis. All right, so to do that, we need to write down the claim. The claim is that it takes, let's see, we're trying to figure out, would this new way perform differently than the traditional method? Would the computer-aided method perform differently than the traditional method? And to do that, we need to say, would the mean not be equal to 95 hours? Okay, and so the opposite of that would be that the mean is equal to 95 hours. So from the sample, we were given that X bar, or the mean, was 94 hours. We're also told that the sample included 170 students. So I know I wrote down a bunch of stuff. Let's go ahead and write down the, let's see, so the one with equality, that's going to be the null hypothesis, mu equals 95. The other one, that's going to be the alternate hypothesis, mu is not equal to 95. If we were trying to find a critical value, then we would use this right here, which will tell us that it was two-tailed. We're not trying to find a critical value, though. We would use the table with the two-tailed answers from the book around page 484 or so. All right. But we're not, so we won't have to worry about that. The test statistic, all we need now is the standard deviation, and that's it. So we were given that the variance was 49. That's the standard deviation squared. That's the variance is 49. Square root of that is 7. All right, so to find our test statistic, we're going to have z equals 94 minus 95. That's X bar minus mu, the claim, over sigma, that's 7, over the square root of 170. So when you do that, you get about negative 1.862629, whatever. So round that to two places. That's what we do with the z-score. That's the test statistic. We round up to two places, negative 1.86. Right? That's your answer. Okay. Go to problem number 8. Looks like we're just trying to find the null and alternate hypothesis, and it looks very similar to a problem that we have worked before. It says that we have a banana chip manufacturer like to know whether its filling machine works correctly at 416 gram setting. It's believed the machine is underfilling the bag. That would be less than 416. All right, so this one's pretty easy, right? Write down what's given. Mu is less than 416. Write down the opposite of that. That will be greater than or equal to 416. The null hypothesis will be the one with equality. So that mu is greater than or equal to 416. And the other one there, that'll be the alternate hypothesis. Mu is less than 416. All right, that's your two answers. Problem number 9. We're trying to find a test statistic. So we need to see how large is the sample. It says a sample of 11 is made. Well, that's very alarming because that's less than 30. Now keep reading to see if it tells you that the sample is normally distributed. It says, assume the population distribution is approximately normal. So yes. Okay, so this is still a Z. If that statement would not have been in here, it would be a T distribution. But that statement is given. It's approximately normal. So we use the same formula that we used on number 7. Probably want to write down all of that important information. The lumber company is making doors that are 2,058 millimeters tall. If the doors are too long, they must be trimmed. If the doors are too short, they cannot be used. Okay, so a sample of 11 is made. It's found to have a mean of 2,043 with a standard deviation of 25.0. A level of significance of 0.05 will be used to determine if the doors are either too long or too short. So since it wants to know too long or too short, it doesn't matter if they'll be used or not. It just wants to know, are they too long or too short? Okay. So either it's going to be equal to 2,058 or it's not. So is the mean, we have mean not equal to 2,058. The opposite of that would be mean is equal to 2,058. Okay. So that means that our null hypothesis is mean equals 2,058. And our alternate hypothesis is the mean is not equal to 2,058. Now, what else was given in the problem? We were told that we used a sample of 11 doors that were normally distributed. We're given that they had a mean of 2,043 with a standard deviation of 25.0. So it didn't give us the variance on this problem like it did on problem number 7. It just gave us a standard deviation, which is good. That just means we don't have to do anything to it when we plug it in our formula. Okay, so our z-test statistic is going to be, remember, it's x bar minus mu over sigma divided by the square root of n. So that's 2,043 minus 2,058 divided by 25, that's the standard deviation, over the square root of n, which was 11. Right, so find the difference there. Looks like it's negative 15 in the numerator. Then you can flip this and multiply. So you can say it times the square root of 11 divided by 25, or just work it out how you know how to work it out. And you should get around negative 1.98997. You can stop really after the second digit because this test statistic is a z-score. So that's going to be equal to negative 1.99. I believe the problem says 3 decimal places, so let's just do 3 decimal places to say why. Well, it says so. So that would round that up. That would round that to 9. Um, there is a couple of your critical numbers that are carried out to 3 digits, um, to be more precise. And so, since the critical values are carried out to 3 digits, the test statistic being carried out to 3 digits is okay too. It just do whatever the directions say, really. Okay. Problem number 10. A lumber company is making doors. All right, so it's another lumber company problem. It's making doors that are 2,058 millimeters tall. If the doors are too long, they must be trimmed. If the doors are too short, they cannot be used. A sample of 20 is made. Kind of alarming. It's less than 30. And it's found to have a mean of 2,069 millimeters with a variance. They didn't give us a standard deviation. Be careful with that. The variance of 900. A level of significance of 0.1 will be used to determine if the doors are either too long or too short. So again, too long or too short. We're not worried about too long. We're not worried about too short. We're worried about both together. Okay. Assume the population distribution is approximately normal. Is there sufficient evidence to support the claim that the doors are either too long or too short? Okay. So it's good. It told us it was approximately normal. The n was less than 30. So when that happens, either it's approximately normal or it's a t-distribution. So if it's approximately normal, it's still a z-distribution. All right? And so we're going to use that same thing here that's for our test statistic. What is the problem asked us to find? Assume the population. Find the value of the. I think I pushed the problem back. Yeah, okay. It says, is there sufficient evidence to support the claim that the doors are either too long or too short? So we have to go through the whole thing. Either there's not enough evidence or there is enough evidence to support the claim. Okay? So that means we have to do everything. We have to find the null and alternate hypothesis. So in the claim, this, remember, is equal to or not equal to because it was too long or too short. It just so happened that the mean was the same as our other problem. So the claim is that it's not, we're trying to figure out if it's not or not, that makes no sense. But all right, the opposite of that is 2058. So that means that the null hypothesis is going to be mu equals 2058. The alternate hypothesis is going to be mu is not equal to 2058. Other stuff that's given in the problem that's important are sample mean was 2069. Our n was 20. That was the number of samples, that was the number of doors in the sample. We were given a variance of 900. Take the square root of that, you get 30. How do I know that? 30 times 30 is 900, so square root of 900 is 30. And the significance value, the level is 0.1. All right. So we need to figure out a couple of things. We need to figure out the value for the test statistic. We need to figure out the critical number. And then with those two, we can figure out if this thing is going to be accepted or if we will reject the null hypothesis or fail to reject the null hypothesis. Okay. So if this thing is two-tailed, whoa, how do I know it's two-tailed? This thing right here, or no, not that one. Look at the null hypothesis. Right here, you have not equal to. That tells you that it's two-tailed. So look around page 484 for that table that I was talking about, and you will see that your critical value, so your critical Z is equal to, since it's two-tailed, it's going to be 1.645. really that or negative 1.645. Because it's two-tailed, the critical values are on both sides. That's what two-tailed means. So there's a z right here of 1.645, and there's a z right here of negative 1.645. And if our test statistic lies in either of these regions, so if it's greater than 1.645, or if it's less than negative 1.645, then we will reject a null hypothesis. If it's in between these two, though, we fail to reject the null hypothesis. So we need to figure out the test statistic to do that. I wrote down the formula for the test statistic first. That's z equals 2069 minus 2058 over, we have a standard deviation of 30 divided by, let's do the square root of n, so that's the square root of 20. All right, so work that out, flip and multiply, and you're going to get 1.63978, so on and so forth. All right, so we need to at least have it out to 3 decimal places. So if I did that to 3 decimal places, it's 1.639. This is really, really close. That number of 1.639 is less than 1.645. 1.639. So that z-score would be really close to this z-score, but it is in between these two. And so since it is between these two, we accept or we fail to reject 8s of both. Which means that what was our initial claim was that it was not equal to 2058, which made our null hypothesis equal to 2058. So there is not sufficient evidence to support the claim. The original claim is this right here. There is not sufficient evidence to support the claim that the doors are either too long or too short. Okay. So I think that's A, the problem. There is not sufficient evidence. Okay. Number 11 looks like, again, we just want the null and alternate hypothesis. This time we are using proportions. Okay. And the problem states that a newspaper reports that 54% of their readers own a laptop. A market executive wants to test a claim that the percentage is actually different from the reported percentage. Okay, so it's like equal to or not equal to type deal. So they're trying to test a claim that it's not equal to 54%. The opposite of that is equal to 54%, 0.54. So the null hypothesis is going to be P equals 0.54, and the alternate hypothesis is going to be equal to, P is not equal to 0.54. Problem number 12 says a sample of 900 computer chips revealed that 77% of the chips do not fail in the first 1,000 hours of use. The company's promotional literature states that 74% of the chips do not fail in the first 1,000 hours of use. The quality control manager wants to test the claim that the actual percentages that do not fail is different from the stated percentage. Find the value of the test statistic. Round your answer to 2 decimal places. All right. So it gave us the sample information before it actually gave us the literature claim. That's a little different, but so the claim is, I guess, if you test the quality, you're trying to show that it's not equal to. So that would be P is not equal to, that was 0.74. The opposite of that would be P equals 0.74. So that's your null hypothesis, and the other is your alternate hypothesis. Now we want to know the test statistic, and this is about a proportion, so we have a different formula than we do for all the means that we've been working with. And our test statistic for a proportion is equal to p hat, that's a proportion, point estimate, so that has to come from a sample, minus p, that was in our claim, over sigma sub p hat. All right, and what is sigma sub p hat? It's a little different. Sigma sub p hat is the square root of p times 1 minus p. Those are values that come from the original claim, over n, and that n is from the sample, okay? So we have the square root of, here's p, 0.74, 1 minus p, you can do that in a calculator, you get 0.26, and then that's all over 900. So that, remember, is just the denominator of the test statistic. So you have to figure out what that is. I'm going to carry it out a couple places to give me a little bit closer value. So that 0.014621114. So that's what my denominator is going to be. My numerator, remember, p hat, that's the point estimate that comes from the sample. So the sample, it says 900 computer chips reveal that 77% of the chips do not fail. So that proportion is 0.77. So 0.77 minus 0.74 over what we just figured out, that 0.014621114. Remember when you're finding this too, because I've done it in problems, you say this times this divided by 900, then you have to take the square root. Sometimes it's easy to forget to take the square root. I've done it before, so just, pay attention to the square roots when you have to take them. Anyway, so that's going to be about 2.05182338. The problem tells us to round to 2 places. Second place is right here, so that's going to be 2.05. That is our test statistic. Right, problem number 13. A mayor of a town has proposed a plan for the construction of an adjoining bridge. A political study took a sample of 900 voters in the town and found that 59% of the residents favored construction. So that is sample data. Using the data, the political strategist wants to test the claim that the percentage of residents who favor construction is above 55%. Make the decision to reject or fail to reject the null hypothesis at the 0.05 level. So we actually, to do that, we have to go through everything. We need to do the alternate null hypothesis. We need to find a test statistic. We need to find critical values. And then we need to figure out if we reject or fail to reject the null hypothesis. All right, so let's first write down the claim. The claim is above 55%. Now remember, that's a proportion, so P is greater than 0.55. That's the claim. The opposite of that will be P is less than or equal to 0.55. So the null hypothesis is going to be P is less than or equal to 0.55. The alternate hypothesis is going to be P is greater than 0.55. All right. So now, what else do we need? We need that sample data. We were given 900 voters, so N equals 900, and they believe that 59%, okay, that's our P hat, so 0.59 is our P hat, and we will use a significance level or an alpha of 0.05. Remember, we look at the symbol that's in the alternate hypothesis to tell us if it's one-tailed or two-tailed, and also if the symbol doesn't have equality. So this is greater than, so this is a one-tailed with greater than. So you need to go to around page 484, look for those tables, and choose your correct table. That will give you your critical value. I mean, you could do that really quick if you just go to around page 44. You can find your critical z value is going to be equal to, I believe you get 2.41. I'm sorry. Let's see, not 2.41. You get 1.645. All right, so you already have the critical z. We need the test value. So the test value is going to be, let's see, z equals p hat minus p over that sigma sub p hat. So remember, finding that denominator, that's a calculation in itself, so you might want to do that first. So that's found from, remember it was p times 1 minus p over n. So our p in our original claim is 0.55. 1 minus p would be 0.45. And then divided by n, the 900 voters. Okay. Punch that in your calculator, you should get 0.016583123. I'll stop right there. All right, so we need p hat. That's going to be 0.59 minus 0.55 over the number we just calculated. So either store that in your calculator somehow, or you carried out this many digits, that should be good. But we should get something around 2.41200908. Probably just want to carry that out, I don't know, to 2 or 3 digits should suffice. So I'll just carry it out to 2 digits, so 2.41. All right, so what do we have here? We have our alternate null hypothesis. We have our significance level. From our significance level, we got our critical value, knowing that we were looking at the table with greater than. Then we figured out our z test statistic. Okay, so our critical value, remember, was a z of 1.645, and then our critical value was 2.41. It would definitely be greater than 1.645. So that means that we need to reject H sub O. All right, so reject the null hypothesis. All right, these next couple of problems, they have different steps. Now each one of these steps count as 2 points. So that means they each count, I believe it's the same value as, say, the previous problem that we worked. So it's important that you get each step right, because each problem is around 10 points. So take special care on these problems. We're going to work on number 14. And the first step I can see is just to state the null and alternate hypothesis. Okay. So I believe this problem comes from 12.2. So maybe read up a little bit on 12.2 in your textbook or your ebook. It says the bolt manufacturer is concerned about the consistency with which his machines produce bolts. The bolt should be 0.21 centimeters in diameter. That's probably imported for somewhere. The variance of the bolts should be 0.025. A random sample of 29 bolts has an average diameter of 0.2 centimeters with a standard deviation of 0.2236. Can the manufacturer conclude that the bolts vary by more than the required variance at alpha equals 0.05 level? Okay, so first state the alternate and null hypothesis. Okay, so we were given in the problem a lot of information. And a lot of the symbols that I'm going to use are the reason that I use them is because they're used in the formula that we need. Now, since we're talking about variance and standard deviation and things like that, this is a chi-square distribution. So this isn't a z distribution. This isn't a t distribution. This isn't anything like we've done. This is a chi-square distribution. Okay. Our claim then needs to be about the standard deviation. Well, we weren't given the standard deviation. We were given the variance. Remember, we were given our variance was 0.025. So if you take the square root of that, our standard deviation in this problem, you actually have to punch in the square root of 0.025, and you're going to get 0.1581. Okay. So it does say to round the standard deviation to 4 decimal places where necessary. So that's what we're going to round it to. And our claim, it says, can the manufacturer conclude that the bolts vary by more than, okay, so more than is greater than. So our original claim is going to be sigma is greater than 0.1581. Opposite of that would be less than or equal to 0.1581. So that means that our null hypothesis is going to be that sigma is less than or equal to 0.1581. And our null, that's our null hypothesis. Our alternate hypothesis is going to be the other. That's going to be the original claim that sigma is greater than 0.1581. Now, we were also given that there was a random sample of 29 bolts. So n equals 29, where we may need it. We were told that those 29 bolts had an average diameter of 0.2 centimeters. So we're going to call that S, since it's from the sample standard deviation is S sub O. And we're given that as, it's really just S, but your book, your text uses sub O in a lot of these, which you don't even have to. It means the same thing. So S is going to be 0.2236. The average diameter, I didn't write that down. So the average diameter, that is X bar, it told us was 0.2. All right, so just to get everything straight, we have a random sample of 29 bolts. They have an average diameter of 0.2 centimeters and a standard deviation of 0.2236. All right, so we're going to need to find a critical value. We're also going to need to find, well, for this first step, all we needed was the null and alternate hypothesis. So I've actually done more than we need for the first step. You can fill that in. We've already written those down. Then we want to enter in the test statistic. Now, the formula for the test statistic is a little different. Remember, I said this is a chi-square distribution. The test statistic chi is like this, chi-square. It's a chi-square distribution. It is n minus 1, that's 29 minus 1, times, now this value is written like this. It's S sub O squared. So it is the variance from the sample. We weren't given the variance for the sample. So to find the variance, if you have the standard deviation, you need to square that. So that's just going to be 0.2236 squared. So in our formula, 0.2236 squared. All over the variance from the population, which we were given. The variance from the population It's right here, over here with 0.025. 0.025. All right, so if you calculate that, you're going to get something around 55.997. Okay, is that what we were asked for? Oh, we were asked for the critical value of the test statistic. So I just found the next step. I just found the test statistic. This is the test statistic. This isn't the critical value. All critical values, remember, they're going to come from tables. So the critical value, you're going to need to go to the chi-distribution table. So if you pull out your formula sheet, the chi-distribution is table G. The table G, as in gamma. Um, and so to find the critical value, I can probably pull that up on this problem. It is from table G, though. Let's see. We do need to know what our level is here. Alpha equals 0.05. All right, so here's the chi-square table. Remember, what was our n? Our n was 29. So the degrees of freedom, the df, is going to be 28. Remember, n minus, you do degrees of freedom is n minus 1. So the degrees of freedom is 28. And then we had a 0.05 level. Here's the 0.05 level. You go down to 28. All right, so 0.05 level down to degrees of freedom 28. The critical value is 41.337. 41.337. So that is our answer here. 41.337 if you want to know the critical value. It does say around the 3 decimal places. So that's why we need to use 41.337. Degrees of freedom was 28. And use the paper. All right. The next one is the test statistic. That's what we figured out. I apologize for doing that first. That was n minus 1 times s sub o squared divided by sigma sub o squared. So this is sample variance, this is population variance, and this is just n minus 1. And here's the number that I got, 55.997. That's the test statistic. All right, so we have our critical value. I didn't write that one down, but remember it was 41.337. That's our critical chi value. So what that means is, in the graph, it's actually not normally distributed. Chi-square distributions are skewed. This actually goes up and then comes down like that. Somewhere there's a value of a chi value of 41.337, and then anything to the right of that, greater than right here, greater than, so anything to the right of that will fall in the rejection area. So 55 is definitely greater than 41. So our 55.997, that was our critical, or I'm sorry, that was our test statistic, is greater than 41, our critical value. So we need to reject the null hypothesis. Okay, so test statistic, make the decision, reject the null hypothesis. And then, so what would that mean that the conclusion is? So there is sufficient evidence that shows the bolts vary by more than the required variance. Now look back at your original statement there that sigma was greater than 0.1581. All right, and so remember our null hypothesis is less than or equal to. And so if we reject the null hypothesis, then that means that it's not like we accept this, but if we reject the null hypothesis, then this alternate hypothesis, there is sufficient evidence to show that the bolts vary by more than the required variance. problem number 15. This is 12.3. So we are going to look at two different samples and compare those. It says the technician compares repair costs for two types of microwave ovens, type 1 and type 2. He believes that the repair cost for type 1 ovens is greater than the repair cost for type 2 ovens. That's important. A sample of 61 type 1 ovens has a mean repair cost of $69.60 with a standard deviation of $23.47. A sample of 45 type 2 ovens has a mean repair cost of $75.25 with a standard deviation of $15.07 for type 2 microwaves. Conduct a hypothesis test of the technician's claim at the 0.05 level of significance. Let mu sub 1 be the true mean repair cost of type 1 ovens and mu sub 2 be the true repair cost of type 2 ovens. Okay, so he believes that the repair cost for type 1 is greater than the repair cost for type 2. So we're going to be looking at a mu sub 1 and a mu sub 2. So here's what he claims that, or he believes, mu sub 1 is greater than mu sub 2. So the opposite of that would be mu sub 1 is less than or equal to mu sub 2. Okay, so that means that our null hypothesis is going to be that one, and the original claim is going to be our alternate hypothesis. Okay. I believe we just select the boxes here, and this first one here is going to be the null, remember, was less than or equal to. The next one is going to be greater than. Okay. Compute the value of the test statistic. Now this again has a little different formula. You can look in your book. So this is 12.3. Your z value is going to be equal to x sub 1 bar minus x bar sub 1 minus x bar sub 2 over the square root of the variance over n sub 1 plus the variance over n sub 2. Alright, so this is quite a calculation, because you got to be careful. You got to do all these different calculations correctly. You were given also standard deviations in the problem instead of a variance. So you might want to write those down. We were given that sample 1, we'll call that sample n sub 1, was 61. It had a mean of 79.60. So that's going to be x sub bar 1 sub 1, $79.60. And then somewhere down the problem, it tells us that the standard deviation for type 1 was $23.47. And then for the second set of data, the type 2 ovens, we had 45 of those. We had a mean repair cost with x bar sub 2 of $75.25. And then on down in the problem, it tells you that the standard deviation was $15.07. All right, so here's what we need to do for our test statistic. We say 79.60 minus 75.25 over the square root of, you have to say, $23.47 squared divided by 61 plus $15.07 squared divided by 45. Alright, first time I worked this out, I didn't take the square root. So what you might want to do is you might want to work all this out, take the square root of it, write down that decimal to about, I don't know, 5 or 6 places. That's what I ended up doing on this one. The difference in the numerator there is 4.35. The value that I got in the denominator was 3.7519267737. And so then I took and divided that, and that gave me 1.159404. Now it tells around the 2 decimal places in the problem, so this is going to be 1.16. Alright, so let's say our test statistic is 1.16. Okay. That's step 2. Step 3 is to determine the decision rule for rejecting the null hypothesis. So if reject H sub O if Z is, now look back at your alternate hypothesis. The alternate hypothesis is greater than, right? It's the top one here, greater than. So if Z is greater than, and now we have to find the value from the table. This is that same table, around 484. It's greater than, so it's one-tailed greater than, and the alpha is 0.05. So from the table, you get 1.645. So that's what you put in the blank here. So we're looking for if our Z greater than 1.645. Right, so what does all that mean? So that's our critical value. That's actually what that is. So that critical value, 1.645, remember it's a right-tailed. So if our test statistic is in here, we reject. If it's not, we fail to reject. Remember our test statistic? It was 1.16. So 1.16 is less than 1.645. So it's going to be somewhere in here. So that means it will fail to reject the null hypothesis. And so once you have that in, you go to the next step. Make the decision. It's going to be fail to reject because 1.16 is not in the rejection region. Okay, the rejection region would be test statistic greater than 1.645. So like if my test statistic would have been 1.8, 2, or 3, then I would reject. But it was less than 1.645, so I failed to reject the null hypothesis. 2 problems left. All right, problem number 16. This is from chapter 12, section 4. A major oil company has developed a new gasoline additive that is supposed to increase mileage. To test this hypothesis, 10 cars are randomly selected. The cars are driven both with and without the additive. The results are displayed in the following table. Can it be concluded from the data that the gasoline additive does significantly increase mileage? Okay, so if there's no change, it would just be a change of 0. But does the additive increase mileage? Now it says let B, and this is the difference between the two, equal gas mileage with additive minus gas mileage without additive. So what you have to do is you have to take car 1, car 2, you have to take and find the difference for all of these cars. All right, that's going to be important. And write all those down because we're going to need those values. How will we need those values? Well, you can see that we weren't given a standard deviation in the problem. But the formula that we use is going to call for a standard deviation. So yes, you're going to have to figure out the standard deviation of the differences. So what I did on this problem, on the bottom there, I wrote down the difference. It would probably be easier. All right, so here's car. I'm not going to read populate this whole table. But there's your 10 cars. So car 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I really don't need columns this big. All right, and then the difference. I'm just going to say D for difference. So the difference is additive minus without additive. So do that for each car. I did that on my paper. I got car 1, 3.1, car 2, 0.3, car 3, 1.3, car 4, the difference is 0.3, car 5, 1.2, car 6, 0.7, car 7, 2.4, car 8, 3.3, car 9, 2.8, and car 10, 2.9. So that's the difference D. Now, why do you need that? Again, you're going to need that for the formula when we find the test statistic. It asks for the average of the changes. How do you find the average? Well, you add them all up and you divide by 10. When you do that on this problem, you get 1.83. So again, X bar sub D is just the average or the mean. I keep saying average, mean of all of those differences. And then also in the test statistic, we have to find the standard deviation of those differences. That's sub D, not sub A. Sub D. All right, so how do you find standard deviation? Well, how do I find standard deviation? I've done it so many times that I don't do it out by hand anymore. I just plug the numbers in a formula in a calculator. And so you can do the same. I would suggest that you do the same. If not, it is going to take you a while to figure out the standard deviation. My standard deviation that I got that I'm going to use when I round it to 2 places, because that's step 2 on this problem, is 1.19. You can get more places if you need, but that's by using the formula. I think it's in chapter 4, sample standard deviation. All right, going back to the problem. Well, step 1 was to do the null and alternate hypothesis. I was just showing you how to find some of the other stuff we're going to need down the road. The null and alternate hypothesis are about mean changes, or we're about gas mileage. So gas mileage, we're going to have either the mean is going to be greater than 0, the mean change, so that would be like U sub D, is greater than 0, that means there was some change. Or U sub D, the mean change is going to be less than or equal to 0. That's the opposite. The one with equality then would be your null hypothesis. So it's going to be mu sub D is less than or equal to 0. Remember, we're talking about a change. That's why we're using the number 0. That's a little confusing. Either there's no change, or there's going to be, or there's, I guess the change could be equal to or less than, or the change could be positive by using the additive. Usually, though, think about it, usually you get better gas mileage if you use the higher gas. It's like the higher, I guess, a gas with a type of additive. That's why it costs more money. So that's your 2, the alternate and null hypothesis. And that, all these other values we're going to be using. All right, the standard deviation. I told you that. How did I get that? I punched all these differences, all these numbers here, right here, into a calculator and got that. You can go through the long process of doing it if you want, but you should get 1.19 if you round to 2 places, like the problem asks. It's just around the 2 places. Okay. Step 3 is to find the test statistic. And the test statistic, remember, our sample was of 10 cars, and we were not told it was normally distributed. So this is a T distribution. Our formula that we use is going to be the change in our sample minus the change in our population. Now I'm using lowercase v here, so I should probably use a lowercase v for this standard deviation. That's over the sample standard deviation divided by the square root of n. And so if we plug in our values, that's 1.83 minus 0, remember that was what was in the claim, no change, over 1.19 was our standard deviation divided by the square root of 10. All right, and so I believe this is step 3. It asks us to round to 3 places, get 4.8629. So the third place would be right here, so that's 4.863. So right here we're looking for 4.863. Step 4, we need to figure out the rule. This is going to be the critical value. Okay, so look at the alternate hypothesis. The alternate was greater than, so you need to go back to that table. No, actually, we need a t-table. So the t-table is table D on your formula sheet, or you can bring it up here, the t-table. And this was, let's see, for greater than, so it's going to be in one tail. We had 10, so our degrees of freedom is going to be 9. And then the area in one tail we use 0.05. So 9 and 0.05 is 1.833. Degrees of freedom is 10 minus 1, so that's 9. And so there were 10 cars. And then 0.05 is our significance level. So that's 1.833. So that's our critical value. Our critical T, 1.833. And it's right-tailed, so remember, the greater than means right, so whenever we're entering all this in here, reject H though if T is greater than, and then 1.833, which is round to 3 decimal places. All right, so make a decision. Okay, so let's make a decision. We have our critical T score. Our critical T is 1.833. So if our test statistic, since it was greater than, is to the right of that, it's bigger than 1.833, then we will reject. Our test statistic was 4.863. So that is most definitely greater than 1.833. So we will reject the null hypothesis. So reject. Okay. The last problem on your test review. We're given these 2 independent random samples with the following results. So you're given an n with a p hat sub 1, n sub 2 with a p hat sub 2. So these are, point estimates. These are sample sizes. Can it be concluded that the proportion found in population 2 exceeds that of the proportion found in population 1? P sub 2 exceeds or is greater than P sub 1. Okay. But notice how it's written down here, P sub 1 and P sub 2. So here's what it said. It said P sub 2 exceeds P sub 1. But when we write it down, we want it flipped the other way. So if you just write the P sub 1 first, you have to write it's less than P sub 2. Like that. So that's how it's given in the problem, how we have to write it. All right, now the opposite of that then would be P sub 1 is greater than or equal to P sub 2. So is that true? I don't know. You can see. But that's going to be the alternate, or I'm sorry, the null hypothesis. P sub 1 is greater than or equal to P sub 2. The null hypothesis, wait, that's the null hypothesis. P sub 1 is greater than or equal to P sub 2. The alternate hypothesis then is the other. P sub 1 is less than P sub 2. Right, so whenever we fill in those, just fill in those accordingly. P sub 1, let's see for 8 of those, it's greater than or equal to, P sub less. All right, so That's the correct answer for that one. Then compute the weighted estimate. Now, the weighted estimate is found in the book. They use a P not here, but that needs to be P sub C, I believe, in the textbook. That's what it's stated as. Okay, and P sub C is equal to n sub 1 divided by n sub 1 plus n sub 2 times P sub 1 hat plus n sub 2 divided by n sub 1 plus n sub 2 times P sub 2 hat. So basically, plug in those numbers to get your weighted mean. And it's a lot of calculations. It is 565 times 0.59 over, I went ahead and added n sub 1 and n sub 2 together, and I got 1,043 plus 478 times 0.73, all divided by 1,043. Now, when you do that, you get out 0.65416,107. It asks for 3 decimal places, so 0.654 is the answer on that one. So that's step 2. Step 3 says to compute the value of the test statistic round to 2 decimal places. The test statistic is going to be z equals P sub 1 hat minus P sub 2 hat over, this again is a lot of calculations, it's over the square root of whatever our P sub C was, which we just got, times 1 minus P sub C over n sub 1 plus P sub C times 1 minus P sub C over n sub 2. Again, it's a lot of calculations, so I'm going to kind of skip some of those calculations. You should get negative 0.14 divided by 0.029561802. And when you do that, you get negative 4.7358. It says to round to 2 decimal places, so round here, so you get negative 4.74 as your critical z value. No, as your test statistic, sorry. As your test statistic. The next step, we're going to find the critical z value. So you need to look at the alternate hypothesis. The alternate hypothesis says that P sub 1 is less than P sub 2. So you need to go to those tables around page 484, look for the less than table, and our alpha was 0.05. So if you find the value there, you're going to find a critical z of negative 1.645. We have a critical z of negative 1.645. So what does that mean? That means that if our test statistic, remember this is on the left, less than is on the left. That's why we have negative values here. If our test statistic is less than negative 1.645, then we will reject the null hypothesis. Our test statistic, negative 4, is definitely less than negative 1.645, so we will reject the null hypothesis. And that's the next step, step 5. Our critical value for step 4 was negative 1.645, and then step 5 is going to be to reject the null hypothesis because our test statistic does lie in the critical region. Best of luck.